3, 2, 1.
My thesis is based on estimating age and metallicity of globular clusters, particularly NGC2808. This thesis is based on calculating age and metallicity of the NGC2808 globular cluster using the Python language and its libraries like NumPy, AstroPy, Matplotlib, and softwares like Jupyter and VS Code. So let's start. So what exactly is a globular cluster? First of all, globular cluster is a cluster of stars, and globular cluster is particularly has its name for being the oldest celestial bodies of our universe. These are one of the most massive celestial bodies, and so generally globular clusters age up to few billions of years, and they have few thousands to millions of stars. Globular clusters are mostly found orbiting galaxies in their halo regions. For example, one of the globular clusters in our Milky Way galaxy is the Omega Centauri. It is one of the most largest and oldest globular cluster in our Milky Way galaxy. Now, the selection of NGC2808. Why did I choose NGC2808? Firstly, NGC2808 is one of the most massive and oldest globular cluster in our Milky Way galaxy. Secondly, generally globular clusters have a single generation of stars. That is, all the stars are formed due to a single event. So there are only single generation of stars in most globular clusters, almost all the globular clusters. But NGC2808, particularly NGC2808, is one of the few globular clusters that we know that has 3 generations of stars. That is, its stars have been formed due to 3 different events at different periods of time. Although scientists have researched that have found that all the stars of NGC2808 have been formed about 200 years from the cluster's formation. So we can conclude that all the 3 events that formed these generations of stars, different generations of stars, would have been occurred in the time span of 200 years after the cluster was formed, which is a really small time span. Like if we see in last 200 years, we haven't had any major news about any major cluster forming or any major thing happening in the cluster. So it is a really big thing that NGC2808, after it was formed, within 200 years 3 different events occurred in its in or around it, and which formed its 3 different generations of stars. Moving forward, NGC2808 is about 12.5 billion years old. It has more than 1 million stars. Its magnitude is 6.2, and it is situated in the Carina constellation. Now, why do we need to calculate age and metallicity? What would it help us to gain? What would it help us to research or to find out? Age, as we know, tells us when the globular cluster or a celestial body was formed. But we can also find out from it that when its galactic components were formed, which would help us to know many things about our universe which are still unknown. Metallicity, as we know, is the amount of metal content in any celestial body. So metallicity helps us in determining the chemical environment around that particular body during the time of its formation. So together, when we combine age and metallicity and its results, we can know that what chemical things or chemical changes or chemical environment or enrichment is changed, is determined, is developed since the time of its formation. So, for example, if we take NGC2808, which is about 12.5 billion years old, as we saw earlier. So when we take age and metallicity of NGC2808, we can find out from that the key when when it was formed 12.5 billion years old, after that at different periods of time what chemical changes happened inside or around that cluster. So it would help us in that, which is the goal of our thesis, to analyze age and metallicity, and for future to know how the chemical enrichment was changed. Now the general trend is that older clusters have lower metallicity while younger clusters have higher metallicity. So the simplest explanation for this, to understand it simply, we can say that as we know, all the clusters are formed from gases, from the gases that were around here during the time of our formation of our universe or the formation of celestial bodies. So we can say that younger clusters were formed from the gas which was at its high metallicity and which was metally enriched, which was really enriched with metallicity, which helped to form these clusters with higher metallicity, while the older clusters were formed when this gas was in its developing state. So it itself didn't have that much of metal content, due to which the older clusters could not have much of metallicity, so they have lower metallicity, while the young clusters have higher metallicity. As we can see here, older clusters have fewer heavy elements due to their lower metallicity, while the younger clusters have high level ISM, that is the interstellar medium. Now, for this research, for my thesis research, I have used the data from the Gaia spacecraft. This is an astrometric spacecraft that was launched by the European Space Agency back in 2013 to understand our Milky Way galaxy in all the 3 dimensions. Its orbit is around the L2 Sun Earth L2 point. As we know, our ISRO agency has ISRO organization has launched the Aditya L1 for the L1 point around the Sun Earth. So it's around the L1 point, around L2 point. It's the Gaia spacecraft which is there. Now the main instruments include the astrometric, photometric, and the radial velocity spectrometer. Astrometric instruments include they analyze the positions, parallaxes, proper motions of the celestial bodies, while the photometric instruments analyze the light in its 3 bands, G, BP, and RP, while the RVS analyzes the radial velocities and also the spectra of the bright stars. As you can see here, this is the Gaia spacecraft. This is the RVS, radial velocity spectrometer, and this is the blue and red photometer. These images were released by the Gaia scientists and the European Space Agency for public usage and public knowledge. Here the BP-RP index is particularly important, as we have used it for our own colorimetric diagram, for my own colorimetric diagram, which was the key point of the research, and for determining age and metallicity. Data source, as we saw earlier, the data was used from the Gaia spacecraft, namely the dataset was the Gaia ADR3 dataset. This is the most recent dataset released by the European Space Agency for public research, or for researchers like me, students like me. And the older data sets that were there were DR2, Gaia DR2, and Gaia DR3, which were also really good, but particularly Gaia EDR3 has more astrometric data, which helps us in determining these things very accurately. The initial dataset was downloaded in the votable format. Then I analyzed it using the AstroPy library of the Python. The initial data from it, the my important parameters were the proper motion in right acceleration and declination, namely PMR and PMDEC. Then the RUWE, which is known as renormalized unit weight error. The simplest example for RUWE would be that the more clues the RUWE is equal to 1, the more high quality data of that particular body or star would you have. So if RUWE is exactly equal to 1, then you have really got good quality of data. So it was filtered due to that. Then the GBP RP magnitudes, these were used for CMD, and the workflow was like, first I passed the votable format, then I filtered them out to gain my stars. I used Python and its libraries like NumPy, AstroPy, and Matplotlib, and it was done in the software Jupyter and VS Code. Now the de-reddening photometry. De-reddening is the effect where the stars appear dimmer and redder than they usually are. So it is because of the dust components around them and in the data set. So I performed the de-reddening photometry to get the dust out, and get the most accurate stars and its redness. So the color axis value I used was taken from a paper by a renowned scientist Wesley. So I took it from there. Then the Gaia specific extinction coefficients were applied. This is provided by the Gaia scientist, by the European Space Agency. So I used these equations from there, and then the magnitude and color axis equations were also applied. This then left me with de-reddened data. Now for the isochrones, which is really the core part of my analysis, I used the Parsec models. Parsec models are the standardized models for isochrone fitting. Parsec stands for the Padova and Twist stellar evolution code. So these simulate stars within wide ranges of mass, age, metallicity, etc. So the first plot I made for this analysis was the vector point diagram, the proper motion vector plot. So these show us the sky positions of the stars RA and DAC. RA, as we know, RA is like the latitude and DAC is like the longitude. So the red point here in the middle, you can see, is the direction of the mean motion of the cluster. This is the mean motion of cluster, and the direction it is pointing is the direction of the cluster. The direction of its motion, the motion direction of the cluster. These stars around it that we can see are the probable members of our analysis that we have got, and among these stars, many stars point towards the opposite side, many stars point with the cluster. So we have plotted it for that, to know how which stars could still be of the field, could still be field stars and not the cluster members. The conclusion we got from here was that the stars close to the mean direction, cluster mean motion, were the most probable members of our cluster. Then comes the de-reddened CMD, the de-reddened curl magnitude diagram. Its x-axis contains the G magnitude and the y-axis contains the BPRP color index. This was plotted after the stars were filtered out with the phi sigma proper motion and the de-reddening correction. So this was plotted after that. Here we can see this tight vertical sequence is the main sequence, and this is the red giant branch. The de-reddening shifted stars more towards the bluer side because it excluded the dust particles. So we were left with these stars, and these scatter points could be signifying the contamination stars, or the measurement errors could be there, which were represented by these stars. Now comes the core of our analysis, the isochrone fitting. This isochrone fitting, as we know, was done using the Parsec model. I compared the grid of Parsec isochrones with the CMD, and I got this red curve on my CMD diagram. This red curve has a fit score of 0. No. This red curve then showed me the best fit isochrone, which is this one. The best fit isochrone showed me the calculated age. It's like most stars were included in this one. As we know, it doesn't take account into the mass factor. I applied robust membership selection, many filters like NAN filter, RAWE, proper motion, etc. to get these results. The deraded CMD diagram was constructed for the accurate analysis, and the CMD diagram was really close to the best fit isochrone, which confirms the reliability of our results. And these results are really close to the literature. The literature really consistent with the literature, so the methodology and all is really reliable. These are the literature that I used for this analysis, and some values were taken from these literature. I would really like to thank and acknowledge them. I would also like to thank my supervisor, Dr. Nitesh sir, and my co-supervisor, HOD sir, for their unwavering support. Thank you.